Today we're going to discuss the last section of Chapter 11, which is about atomic properties and the periodic table. Okay, so metals are one of the first parts of the periodic table, and they have several properties that distinguish them. So they're usually lustrous, which means that they're shiny. They can change their shape without breaking, and two examples of that are the fact that they are malleable, which means they can be hammered into thin sheets, and they're also ductile, which means they can be pulled into wire. And they are also, for the most part, good conductors of heat and electricity. Okay, so we've got all of our metals in blue over here. So metals take up most of the periodic table. So they're on the left and the middle of the periodic table. Metals will also lose electrons to form positive ions. So if you remember when we talked about charges of ions before, this first group is a +1, so it lost 1 electron. The second group is a +2. You've got all our transition metals that are positively charged, and this group is a +3. So they're losing electrons to form positive ions. Okay, the next major group are nonmetals. They're pretty much the exact opposite of metals. They're usually not shiny or good conductors of heat or electricity, and they're located in the upper right-hand corner. So right here, these are all of our nonmetals, plus we've got hydrogen. They tend to gain electrons to form negative ions. Okay, so if you remember, we've got noble gases, and then we've got a -1, -2. Okay, so they will all gain electrons. When metals and nonmetals react, one or more electrons is transferred between metals and nonmetals, and those are specifically ionic bonds and ionic compounds. Okay, the third type are metalloids. Okay, well, metalloids are kind of a combination of metals and nonmetals. So they exhibit some properties of metals and some properties of nonmetals, and they're located right in the middle along this stair step. So they're this purple section. Okay, well, not all metals are alike. Okay, so some will lose electrons much more easily than others. And so if we look at group 1, which is the one highlighted in red here, cesium will lose its electrons much more easily than rubidium, potassium, then sodium. Lithium hangs on to its electrons the most. As you can see, this trend goes this direction. Okay, so cesium loses its electron most easily, and lithium is least likely to lose an electron. So what this means is that as we go down the group, they're more likely to lose electrons. And part of the reason for this is because if you remember when we talked about electron configuration, as we add more electrons to the atom, they get further away from the nucleus. So way down here at cesium, we have a lot more electrons than lithium, and so those outer electrons, those valence electrons, are further away from the nucleus, and they are more easily lost. Okay, well, not all nonmetals are alike either. Nonmetals with the strongest pull on electrons are in the upper right-hand corner. So the most chemically active metals are the lower left-hand corner, like cesium, because it easily loses its electrons, and nonmetals are in the upper right-hand corner, so they're kind of on opposite ends. So this relates to certain trends that we see on the periodic table. So the first one that we're going to look at is atomic size. As we go down a group, this direction, our atoms get larger, and you can see from this picture that we've got the biggest atom at the bottom here. This is because we're adding more electrons. Okay, and as the electrons get further from the nucleus, there's less pull by the nucleus. They're not as pulled in, and so they take up more space. Atomic size will also get smaller as we go from left to right across the period. So if I was drawing my arrow towards the larger ones, I would draw my arrow this direction. This is the biggest element, and up here is the tiniest element. Okay, and so the reason they get smaller as we go across towards the nonmetals is because as we go across, the number of protons increases, and these create more pull on the electrons. Okay, especially up here, we don't have many electrons, and those protons are really going to pull on them, keeping them in really tight and small. Okay, let's look at the second trend, which is ionization energy. Okay, ionization energy is the energy required to remove an electron. We're turning it into an ion. Remember, you can change electrons. That's what makes things ion. So if we're removing an electron, we're making it a positive ion. Okay, and so metals have low ionization energies because they want to become positive ions. So it doesn't take a lot of energy to remove their electrons. They want to get rid of them. Okay, so ionization energy will decrease going from top to the bottom of a group. And so cesium, we talked about, is the biggest, one of the biggest, and it also gives up its electrons really easily. So it doesn't take a lot of energy to remove its electron because it wants to get rid of it anyway. So this is a very tiny ionization energy. Okay, and then it increases as we go up the group. Now let's talk about horizontal. Well, nonmetals have very high ionization energies. They want to become negatively charged ions, and so they don't want to give up their electrons at all. So they're going to make it really hard to remove one. So ionization energy will increase as we go across because those nonmetals want to hang on to their electrons, especially the ones in the upper right-hand corner. We said these were the most active, so they are not going to want to get rid of their electrons at all. So their ionization energy is going to be huge. Okay, so very tiny, really big. So the lower the ionization energy, the more it wants to give up electrons. And it seems a little backwards, but if you remember the definition for ionization energy, this will make sense. It's energy to remove an electron. All right, our third trend is electron affinity, and this kind of goes with ionization energy, except it's kind of opposite. Electron affinity is the ability of an atom to accept an electron. If you have an affinity for something, that means you like it. Like you have an affinity for chocolate, that means you really like chocolate. So electron affinity is when atoms take on electrons. This is the opposite of ionization energy. Energy gained when an electron is accepted by an atom in the gas state to form an anion. That's the technical definition of electron affinity. So the more positive the electron affinity, the greater its affinity for electrons, or the more it wants them. So remember, our nonmetals up here want to be positive ions, negative ions. They really want electrons. And so when they gain one, that is a positive thing. So they are hugely positive. Okay, well, metals are going to be the exact opposite. Cesium and francium and all those down here want to give up their electrons. So if they have to take one on, that's really a negative thing. Okay, so very big but very negative. Up here in the nonmetals, very large but very positive. So we would say it increases as we go up and across. Okay, so here's a summary of all the periodic trends that we talked about, as well as the metallic and the non-metallic character. So usually what I do is draw a box representing the periodic table. Big circle down here representing big atomic radius. Tiny circle up here representing super tiny. And if I know where those two are, I can figure out the trend. Ionization energy is the energy to remove an electron. Here it's going to be extremely small because it wants to give up its electrons anyway. Whereas up here we have a huge ionization energy. Okay, it does not want to give up its electrons under any circumstance. Okay, our third one is electron affinity. How much an atom wants electrons. Well, these metals, especially down here, don't want it at all. So it's very big and very negative. Okay, whereas these metals up in the upper right-hand corner really want electrons. So it is very big and very positive. And so if you can remember those three trends, as well as explain why they occur, so understanding the definitions, you'll have no problems. Okay, so here's some homework. We will work on it in class. Otherwise, have a good day.